Hello, here's Zhenghao Li, and this is my presentation in final project medical imaging in the course COMS 4995 Applied Deep Learning. And my goal is to detect cancer metastasis on gigapixel pathology slide. The challenges are human can be tedious and error-prone. Tissue samples are volumes. Each image is high resolution. Expertise is rare. Tumors can be small, needle in a high stack, and fatigue. Then first I need to introduce my processing. First, I transfer data from Google Drive to Google Cloud Storage. Then I download data from storage to my code lab and make sure everything works good in starter code and data. Make sure patches and labels are well. The left side is non-cancer patch and mask. And we can see it works well, and there's no yellow means there's no cancer cell. In the right side is cancer patch and mask. The yellow part means the cancer cells, cancer pixels, and so it works well. Let's go through my code. First, install all the libraries, open slide, then import all the libraries, the OpenLight, NumPy, and especially the TensorFlow, and some math random. And this is authenticate user for download data from my storage. This code is for downloading data from my storage, and here is all the slides and 2 more masks, except some slides without masks. I can not train them because they don't have labels. After download all the data, I need to check if everything works well. This is I opened all the slides and max to see their levels and dimensions, and well, it works well. There's lots of them. Then I write all the useful functions which we'll use in the later work. The rate slide, and this is plot tumor slide, plot tumor mask, this overlay slide and the tumor mask. And let's random choose 2 slide and mask to say what will. This is in the start code, and we can say the result is the same as the start code. And here we random choose 1, and it also works good, so it seems our data goes well. And this is little tips from starter code to improve efficiency by ignoring non-issue errors of the slide, and find non-tissue errors by looking for all gray regions. And we ignore the regions the gray is over 0.8. And this is pre-processing to slide to get patch from slide. We go through every slide, then go through every slide in its while, then go through every slide in its head. Then we read slide each patch and each slide from the slide, and then we need to find all the tissue pixels that is the gray is over 0.8, and if our tissue pixel is over 1000, we need to take these regions. Otherwise, we don't use this patch, and we still need to save the mask of this patch to do a label, and we calculate all the cancerous cell in this patch. If the cancerous cell is more than 1, and we label this patch for cancerous, which means we label it 1. And this is we show a single patch, and it seems it works well. And this shows we have 26,000 patches, and 3,000 of them are cancerous patches, and 23,000 of them are non-cancerous. And we need to say if our labels are correct or not. This is an example of cancerous patch, and we say the mask works well. It's just like shown in my slide. And the example of non-cancerous cell, and it also works well. Then we need to split. The approach of mine is to implement an end-to-end prototype. First, I start with a low Doom level 5, and I collect data set by sliding a 75 × 75 image across each side. The street is also 75, so consecutive patches are neighboring but not intersecting. Just shoot in this. And I display all the patches that contains less than 1000 non-gray pictures, just like this. And I labeling dataset. Each patch is labeled 1 if it contains at least 1 serous pixels. If not, then labeled error. So just like this one. And after these steps, I continue to split the dataset into train, validation, test in this radio. Here is the code. I randomly shuffle the cancer regions and split them and label them. And then I split the non-cancerous patches and then label them with arrow. And I calculate, and then I transfer learning from Inception version 3 trained on ImageNet, and then output heat map on one of test images. And first, I tried only on Inception version 3 first, and I didn't do any argumentation, and I just train it, get results, and just do a heat map. And all this I have deleted them from the code now. And after I complete my implementation, the end-to-end prototype, I just get up to a middle doom level 4, and I augment training data. And first I run the code to here. I calculate the ratio healthy divide by cancerous patches, and it's 7. There are 7 times more non-cancerous patches than cancerous patches in training set. So to each cancerous patch, apply vertical flip and or rotations by 90 or 180 or 270 degrees for each such patch, then balance the data set ratio around 1 to 1. Here is code. I just expand the cancer train data, rotate 90 degrees, rotate 180 degrees, and flip, and flip and rotate again. Then I get all the data I need, I balance them, and the ratio is around 1 to 1. After that, I just mix them up, and here is all the data for train and the label. Here's the data for validation. Here's the data for test. I just concatenate the cancer and non-cancer data. After this, the size of training data is 30,000, and the validation is 8,000, and the test data is 6,000. And then I tried the different model from the first time. I used ResNet 50 because the later model works well. So I choose this one, and the transfer learning from the ImageNet. And I do a fine tune. I add a later dense layer, and then use RMS with learning rate of 0.0001, and compile it. Here's my model, my final model. And my model, I trained the entire model with the dense layer on top of size 32 and customer optimized RMS, which has a small learning rate of 0.0001. My best result on validation data is here. It's 0.96. This seems very good. And in training, data is 0.99. And I plot this learning rate and loss. Actually, we can say here's a trend of overfit. The validation accuracy goes down, and the loss goes up. After that, I evaluate the model in test data, and I get a very well accuracy of 0.98. Then I save my model, and because if I run from the start to the end, the Colab RAM will be run out, and my program will crash. So I need to save the model upstream and load model. Then I output my heat map. This is the function I use to create heat map. After train model, I built a heat map that the regions of the whole images are likely to be cancerous based on model. I slide the patch over the image if the model predicts the patch to be cancerous, make the whole patch red, otherwise make the patch white. Patches that have less than 1000 non-gray pictures are not run through the model. Well, because I didn't train them from start. First, I just this is the white patch, this is a red patch, and here is the background, and here is I go through the height, then go through the white. I read them, and if there are over 1000 cell pixels in this patch, then I will predict this patch. If it's over 0.5, then I think there are at least one cancerous cells in this patch, so I make it red. Then if there are none of cancerous cells in this patch, I make it white. And this is the result. I tried it in the image in starter code, and this is it. Looks like it, and I overlay my predictions and the tumor mask, and so it works very good. But there are lots of normal cells predict as cancer cells, and I tried them in some very obvious. I applied my model in train resolution of level 4. Here's the 3 results. Just looks very good, and we can say our prediction covered all the area of cancer patch. There are hardly cancer cell be missed, and as for why I applied this in smaller resolution level 5 is because if I apply them in level 4, the collab will run out of the RAM and crash. And we say this result works, not that bad, but actually it's not as better as applied in the same resolution. We can say there are little cancerous cells be missed, but actually the most problem is very little run predictions on tumor cells, but many run predictions on normal cells. Yeah, at least this could be good news if we used my model only for assistant only. Then the doctor won't miss any patient. And here's a clear trend of overfit is a very big problem. I think I need to try some new techniques to make it not overfit. And as for my approach, I just trained on all data, but not test on a totally new image. And my project will use for the completely new image. It means when in my approach, I splitting the data only on patches, not on origin data. So although there's some new data for my model, but only some patches, not entire images is new. So I think this could be a problem. And in the future, I will experiment with more architectures, the huge and little structures, and I will try more effective technicals for data extraction like segmentation instead of comparing picture intensity. And that's all. This is all my project work. Thank you for watching.